All right. And so last time we talked about 1D motion problems with word problems, and we kind of hinted at a problem. I think it was 2.13 that was vertical motion. So let's take a look at another one to start today before we get into plots. I'm going to share a screen. And so I'm most interested in this one right now. And so I want to learn everything I can about this problem. All right. And so I'm going to draw it up on the board. You could draw it up on the board, however, or on your notes, and then we can compare our pictures in a minute. So don't look at my screen for a minute and see if you do the same thing that I do. Okay. 2.15. This is on page 28, page 28 in the workbook. Okay. So I just kind of started drawing this up. Your picture might look a little bit different than mine. That's okay. And then if I turn this one way or the other, I get a little less glare. So I'll just do that. So, oh, what did I forget to write up? The problem number. That's a big deal. I always write the problem number. Got to be able to track your work. So we were told that this is a negligible height in the problem. The problem said something like, blah, 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 blah. Assume Jackie's height and air resistance are negligible. So that's, she initially has a negligible height. Also, air resistance is negligible. So those are two key assumptions that are probably worth writing down and getting those on your paper. That way, if somebody says, oh, did you worry about air resistance? And you'd spend a week or two, you could come back and say, oh, no, I didn't on this one. That's all that's for. Just being neat. Did you ignore the height of the person? Oh, yeah, I did. That kind of stuff. It's for helping you communicate with others. All right. So far, so good. Now, this is a piece that maybe you didn't think to draw. And that's partly because maybe it's been a few days. And we talked about this last time with the ball being thrown up in the air on question 2.13. But here, to be clear, G is 9.8 meters per second squared. It's the magnitude of accel due to gravity. And you could get extra practice with what G means in question 2.14 after class. Now, so remember, to be clear, I'm going to emphasize this. G is always a positive number. It is the magnitude. Magnitudes are positive. Notice gravity pulls downwards, right? So acceleration would be negative, but this is not the acceleration. It's the magnitude of it. And you have to get used to thinking of G as just this positive number and think of the plus minus signs as coming from these two arrows up here. All right. So I forgot what we're looking for. Determine max height. So that's our goal. All right. So in this case, I'm going to write down my list of knowns and unknowns. Okay. And then just to keep it slightly interesting, I know some of you don't like talking and it's cool, but the more you talk, supposedly the more engaged you are and the more you remember this stuff. So, I mean, people miss these things all the times and it's your first day. I expect some of you to make some mistakes, but by making them in lecture with me, you'll remember it better and then you'll score better on the quiz. So maybe let's see. Let's have somebody here. What is delta y in this case? Do we know it or do we not know it? And if we do know it, what is it? Somebody go ahead and give it a shot. It's okay to fail miserably. It doesn't matter.
We do not know it.
Okay. Don't know it. I agree. And that's going to relate to what we're trying to find, right? So, all right. Somebody else. What's v initial y? Oh, sorry, I lost you there.
They only told us
V,
right?
V, correct. And it should be a positive V, shouldn't it? Because it's going with the coordinates. All right. And I think I drew that in blue. So let's keep the color code there in blue. What's V final Y, somebody?
0? No.
0. What? Why do you say it's 0?
When it lands, it's not moving?
No, where is it ending up in this problem? We're trying to get the max height, right?
Oh, at the top. And then
At
so
the
it's going
top.
to pick 0 and then start
That's
going
right.
down.
And that was sort of like this case right here. Whoops. If we shoot this thing straight up, you could see, let's redo that. If we shoot this thing right at the top, for a split second, it's not moving, right? And so that's the idea is if you throw something straight up, it gets slower and slower. So velocity becomes a smaller and smaller positive number. And then it becomes a larger and larger negative number. The only way that's possible is if it's 0 right here at the top. All right. Good job. That's the tricky part. In a physics word problem, usually there's something you have to read the words to get a number, and you got it. That's cool. Somebody else that hasn't spoken up. What's AY?
negative 9.8.
Yep. And instead of doing 9.8, let's call it negative G. Okay. So remember, G is the size of it, negative, because this one's going down and this one says upwards is positive. And then time, do we know the time? Somebody else?
It's unknown.
Unknown. All right. So we got our thing. This is looking pretty typical. 3 things you know, 2 things you don't. Next step would be write some equations. Let's see here. A lot of times I like to leave some space. Okay. So in this case, excuse me, I've got some equations. What's one of the things you want to do really early on when you get your equations written out? Plug in
Zeros.
zeros. So that's going to help us a lot. And then rather than plugging it in, I'm just going to erase it. V final Y is 0. And so that might help us pick our equations. All right. And so at this point, the logical thing is to reread and find what are we looking for? Max height. Basically, what does that mean we're looking for in this case?
Delta Y.
Delta Y. We're looking for how much it went in the Y direction. Now think, what are we assuming here, I guess? I'm assuming that Y initial is equal to 0 here because it said negligible height. So this would be Y final, and this change would be delta Y, the change. And so we could see here in this particular case, max height is actually Y final. But because it said the initial height was negligible, we know that delta Y should equal Y final. If Y initial is 0, think Y final minus Y initial is delta Y. If this goes to 0, then delta Y and Y final are interchangeable in this problem, not always. Okay, so that's great. Which equation looks the best? Somebody else. We've got equation 1, equation 2, equation 3. Which one of those looks like the way to go?
Three.
3, because I know this, I can get that. Is there another way to do it? You bet. Couldn't you get time from this equation? We know this and we know this, so you should be able to get t. Once you know t, couldn't you plug that in and get delta y that way? Absolutely. But usually, I mean, this one's going to take us about 2 lines. This one's going to take maybe like 6 lines. So I don't know. I think it's maybe a little bit easier to do it this way. So any way is legit. Anything you can do. So because this one's going to work, I'm going to erase this and move it up and have some room here to work. So we just found I know that's true. And so now you could do the algebra. You could plug in these numbers if you wanted to. Oops. All right. Well, I guess you could move this over to the other side, but I want to show you this technique. I'm going to move this to the other side first, just because there's a common mistake students make. So I'm going to bring that over here. Like that. Be careful. Negative v squared, remember physics, we got to do order of operations in the math, right? So in this case, that's negative after you squared it. So to be clear, this minus sign is not canceled by that squared. Okay, so we have a minus sign here, which came from, think about this. If v squared, let's say v was 3. This would be 3 squared, which is 9. You'd have to have a negative 9 over here, not 9. So we don't expect this squared and that minus sign to cancel. So to be clear, it's not negative v squared. It's negative v squared. All right. That's all I wanted to point out. And that's a big deal because now this minus sign and this minus sign can cancel. And I could solve this thing. We got it. Check the units. Let's see, I'm gonna switch the sides here just so I have room to check the units over there. Sorry about that. So flipping all that around, I think we find that delta y which I'm going to check the units now. And then don't try to do this in your head, people. Let the paper do the work. Meters. There's one M that didn't cancel. That's the correct units. What are some other ways we could check this result? Let's do some intuition. I have a feeling you believe the following statement. If you throw it faster, it should go higher up, right? So does this corroborate that reasoning? Well, if V is a bigger number, I'd expect to get a bigger number over here. Cool. What if we all went to the moon? Field trip, get Hancock to pay for it, I'll go. Oh my gosh, can you imagine that? That'd be insane. But yeah, I don't know how many billions that field trip would cost. Sounds like a good extra credit question. Estimate the cost. But yeah, if you went to the moon, G is actually a smaller number on a different planetary body. And so if we went to the moon where there's less gravitational force for the same amount of speed, if you have less gravitational force, you should actually get an even higher throw. And that makes sense too. So those are some ways you could check these answers, like the reasoning that I just did. What if? And check the units. All right. And so I think at this point, that's good enough for part, whatever that was, part A or something. All right. And so maybe let's see. I'm going to pause for a sec, go to gallery view so I could see you. Any questions? Is this about right? We probably are rushing a little bit, but maybe some of it's sinking in. Give me some feedback anyway. Good or bad. It's funny, they don't give you a thumbs down, do they? It's too bad they don't give you a thumbs down. I'd always be getting that, right? This is designed for teachers. No, but it looks like, okay, sorry, I'm making jokes here. But yeah, it looks like this is doing about right. Okay, let's get back to it then. And remember that other lecture, you could totally use that other lecture as well. You should totally watch that, people. It was a good one. All right, so yeah. Next, time to reach max height. I think we did this earlier and I already erased the equation. We wrote out the equations earlier. I just ran out. Let me ask you this. If our question is this, so in part B, we want to get time to max height. Do I need to redo this or not? Were these things based on a max height problem?
You can reuse them.
Yeah, so we don't have to start over. We can use these same things, and a lot of the work is already done for us. So that's cool. All right, and so now the time to max height, I think we had an equation that was... I think we know this one, right? And we said that this was 0. And so look, if I plug this in here, trying to solve this for t. So in this case, all I did was I brought this over, made it negative. So now I can divide this by and I get t Now notice I haven't plugged in any of this crap yet. So in the previous problem, I plugged in the crap, then did the algebra. That works great. What we see is you could also not plug in anything and do the algebra. And to be honest, at your stage, this way might be better. Because after a while, after you've done like 4, 5, 6, 7 of these problems, you start to realize every problem is the same if you do it before you plug in and do the algebra. And so it gets easier to recognize when you're making mistakes. That's all that's good for. It's not that any other, it's this, yeah, it's just the more times you do problems in a similar way, the more likely you are to catch mistakes as you make them. That's all. So now in this case, watch what happens when we plug in. It looks like time is negative, right? Oh no, I'm scared. Well, V initial Y, that was V, right? What was AY?
Negative G.
Negative G. And notice the minus signs cancel and it all works out. Life goes on. This plus sign. And notice the units work out. Meters per second. Yes, it's good. I can see it right there. So you can check the units on your own, but I just wanted to show you that's a different style to do. Okay. There's the time. And notice this is pretty typical. It takes forever to get the first part of a physics question. And then afterwards, they're a little bit faster. So nothing beats practice for getting your speed up, right? If you don't practice, you're just so slow. And I don't know, there's something to be said for having some speed. You know, you think about why people hire people in the first place and why do they make you get a degree to be hired, right? It just shows that you can learn things quickly. But for example, if there's a lot of jobs out there that a physicist will be qualified to do, but they'll never hire a physicist. They'll only hire an engineer. Why? Because the engineer has done more practice with the kind of details and the style of doing engineering. So that's why it's hard for physicists to get engineering jobs. So there's something to be said for just doing the practice. That's all I'm trying to say. Enough of that. Let me just check in. How are we doing? I don't see any questions popping up. And remember, Memo, you've got Memo's email if you want to contact him for tutoring. I know some people have been using that. That's good. Memo, you could throw it in there again just in case. All right, let's go ahead and look at the next part and then get on to something else here. Whoops. Thanks, Memo. All right. I'm going to skip part C. I want to figure out part D. So let's say we want, you could do part C at home, but let's say we wanted to do part D. So it says impact velocity when the ball finally returns to the ground. There's lots of correct ways to do this, but this is the one thing I want to point out. If we talk about going from here all the way to here, is this list of crap still valid? No.
Yes. No.
Oh, okay. What were you thinking, Esteban? Tell me what was going on in your brain.
Well, I'm thinking that initial velocity is going to equal final velocity because it started at 0. So I would go straight to that.
Do you agree that that's not exactly the same as this?
Right, because
okay, that's what I was saying. Is that okay? So I think what you were saying was correct, Esteban. He's saying shouldn't the final velocity equal the initial velocity? What goes up comes down, kind of thing. Is that what you were saying?
Exactly.
Yeah, and so I just want to point out then that this is no longer 0. And so moral of the story is this. Thank you, Esteban. That was good work. What you want to be careful for is sometimes part A of a problem talks about max height, and sometimes part C, D, or in this, I guess it was D, talks about the entire flight. So let's just do this. Let's say we're going from the initial position all the way over to here. Okay, so from here to there. So now we're going to do 2.15 D. This stuff is not valid. And what was I asking? Velocity at impact or speed at impact?
It said
Impact.
Velocity.
Okay. So this is something you have to watch out for in a physics question, all right? Impact velocity is the speed right before impact, okay? And notice I said right before impact, okay? The idea is, this is all wrong now. Let's fix that up. It gets very complicated to do problems while impact is included. So like, let's say I had a surface and I dropped this marker. You know that just after impact, this thing stops. You know that just before impact, it's moving downwards. And so typically, if we're trying to learn about the time to impact or impact velocity in a physics class, that means just before it hits the ground. Just before, like the nanosecond before, or 1 atom's width before it hits the ground. There's other physics you can learn for dealing with the collision with the ground. That's later. That's another course. Okay, so just know impact velocity. I want you to emphasize that's just before impact, okay? All right. So maybe we could get some people speaking up here that haven't. So I was just talking with Esteban. So maybe somebody other than Esteban, tell me what delta Y is in your opinion. Again, we're going from here to here.
Zero.
Zero. Nice. Good job. Think about it. The change in Y. And if remember, there's a J hat hidden on all of these, right? So it did go up some distance and then it came down, let's say 6 meters, and then it went down 6 meters. So the net change is zero. Yeah, that's a tricky one. Good job. Hey, what's A sub Y? Somebody else.
Negative G.
Negative G again, right? So that's cool. V initial, I'll do that one. That's still V. G, I wonder what things we don't know. Haven't we seen there's usually 3 you know and 2 you don't? All right. So in this case, we know delta Y, V initial Y, and A sub Y. There's the delta X equation or delta Y equation. Right. And you don't have to write these out all the time, but hey, you're trying to learn this stuff, right? Why not just write them out every time? And then you're just faster because then you'll have them memorized in a week. Okay. So, but that said, if you don't feel like writing them out, remember you got them right here on the back. And so you could just kind of look at them. And if you wanted to, you just say, okay, this is what I know. There's the equations on the back of the workbook. Which one should I use? 1, 2, or 3? Somebody that hasn't spoken up on this problem. So what do you think? Equation 1, equation 2, equation 3. Which one ends up looking the best? And just wait them out, everybody.
The third equation?
Let's see. I have no idea. So let's see. Yeah, let's see. This one looks good, doesn't it? Yeah, actually, because the zeros are going to drop this out. That's a 0. That's a 0. So yes, this one, we know this looks good. Nice. And okay, so let's finish this out. I got to sit down to finish this. It's too low. All right. So this is where it gets tricky. Do you agree I just need to take the square root?
Yes.
So V final Y is equal to the square root of V squared. So are you feeling pretty good with that, everybody? Esteban, don't speak up. What do you think?
But it should be plus minus, right?
Absolutely. Nice. I don't even know who that is, but you're doing a great job. I've heard you a couple times today, so good work. It's weird on Zoom. I can't see who's talking. So anyways, yeah, we need that plus or minus. And in this case, which one makes sense?
The minus.
The minus. Think about it. At the end of the problem, aren't you going downwards? So we need that minus sign right there. So it's actually negative V. And now you heard Esteban and I talk, and we were saying, oh, what comes up must come down. And then it turns out you probably knew this already, that, hey, if it just goes up, isn't it just going to come back down at the same speed? Yes, but the velocity is a different sign. So just be aware, watch out for these words: speed versus velocity, distance versus displacement, position versus distance or displacement. So in a, or always look out for the word magnitude in a physics word problem. You just really have to be reading all the time carefully. What does the teacher want? Imagine in a Canvas quiz, if you do all this work, you got the speed right, but I asked for velocity and you didn't enter the minus sign. You're getting it wrong. That's frustrating. So you got to read carefully. You know this probably already from the first two quizzes, so I probably don't need to say that. All right, but that said, all right, there's that. Let's see how we're doing here. Am I still screen sharing? No, I'm not screen sharing. Let's do that. So just to look at this case, let's do something easier to see. We'll do a pumpkin, and let's slow this thing down maybe to 15. And so the idea here is this. Oops, my zoom's blocking it. So there's the pumpkin. Flies up in the, come on, zoom. Oh my gosh, so many things here. All right, so if we want to, we could go back and let me see if I could do this one and shoot it in slow-mo so you can watch this one. Here it goes again. It's going up, slowing down. It comes to rest for a split second. Now it's got a negative velocity like this. That's great. And so if you really wanted to, where did I put that? Oh, there it is. You could go into here and get your range and things like this. So if you want to play with this sim, I'll give it to you here in the chat in case you wanted to play with that later on your own. Now let's do this. I'll do it this way. There it is. So if you want to play with that on your own, that's great. Also, something I forgot from last time, we keep talking about this air resistance is negligible. I've got something else I meant to share with you last time. So let me see if I can show you where that is. So here's this NASA and the bowling ball trick. So I'll give you the long one. We don't have time to watch this in class, but you should definitely watch this later. It's slightly interesting. It's 4 minutes or something, 5 minutes almost. It's pretty cool. You can see that if you get rid of air resistance, the bowling ball and the feather really do. This experiment must have been so expensive because they had to evacuate this huge multi-story building like a giant silo. Really expensive to show you this. So that's cool. So there's that. And then while I'm at it, oh, where's that one? Since I'm giving out links. This is the 1D motion with the guy that was moving back and forth left and right. And we're going to work on that in just a minute here. So, all right. Yeah. Unless there's any questions, I'm going to start talking about plots now and what these plots mean. Remember, you've got another example already worked from the earlier lecture on the YouTube live stream archive. So, okay. So now we're going to introduce this topic today. And the last half of that other video is probably going to be nearly identical to what we do. So yeah, just be aware of that. So at some point, if you really wanted to take off right now, you could because you've got the other lecture. But I'm going to go through it now, and then you have the opportunity to ask questions. So we're somewhere right around page 31. So I'll screen share in just a sec. Page 31. So you could do up to 2.24 now. And then it turns out a huge part of being a scientist is understanding how to read plots. Okay, so you just have to be good at it. That's just the facts. And so what we're going to do is we're going to plot position versus time, velocity versus time, and acceleration versus time. And to be clear, we're going to be talking about things. There's going to be an implied I hat or J hat. So for today, I'm going to be talking about an object moving left and right. There's going to be an I hat implied on these. So remember, this is position. It is not distance. It is not displacement. It is position. You don't get a choice. This is velocity. It is not speed. Velocity and position can be positive or negative. More on this in a minute. And to be clear, this is going to be acceleration, not acceleration magnitude. Okay. And okay, that's enough on that for right now. Let me give something more. Now, the two most important things that we've got to get out of this page, and you're lucky because during your quizzes, you can have this book open to this information. You need to memorize this stuff, and not just memorize it, internalize it. And by that, I mean, you not only need to know what these words are, you need to know how to use them. And I'm going to give you plots on the test, and you're going to have to be like, okay, which plot is this? Okay, if it's an XT plot, I'm going to come into here, and these are the things I know, and then I'm going to use them. If it's a VT plot, I go to this list of crap that I know, and I know how to use it. And there are so many ways to screw this up. We've got to do at least all of today and next time to practice, okay? All right. There's also the AT graph. And since that's got such a small amount of stuff here, I'm going to do that last. But to be honest, most of the quiz questions focus on XT and VT graphs. So this is the stuff you really need to know. All right. So the first thing is time is on the x-axis and x is on the y-axis. Don't you love physics? And x is position, not distance. All right, so before we get too far ahead of ourselves, let's look at an example. All right, so here it is. I'm going to run this one back. So notice right now, let's just, let's clear this. All right, and so I'm going to start this at -4. Let's say the velocity is +6 and the acceleration is -2. So if you didn't see me type that in, here's our initial values, right? Okay. And what we're going to do is we're going to hit play in just a second. And I do want to point out the following. This, notice that right there, is this number, -4 meters, the initial position. This is 6 meters per second. That's the initial velocity. And finally, all of these plots, it's hard to see, but way down here at the bottom, I don't know if you can see me circling this yet. There's a little lag, obviously. But way down here in the bottom, notice this says 10 seconds. This is the time axis. So this is 1 second. This is 2 seconds, etc. Put a couple of those in there. So the horizontal axis is not X, it's T. Don't you love it? Okay, so that said, let's clear all those drawings and run this thing. Here we go. It moves forward, it moves forward, it moves forward. It's slowing down, it's slowing down, it's slowing. Split second, it stops. And now it's going backwards, going backwards. And I'm going to try and stop this about when it gets to 10. All right, so that's not exactly 10, but pretty close to it. And so there we go. So what are we seeing here? Again, this vertical intercept is the initial position, which was -4. This right here was V initial. That was +6. And I got to be careful. This one is meters per second. And that other one was meters. All right. Notice the final position here is about -10 meters. You can see that's almost all the way over there. All right. And for this one, it looks like the final velocity is maybe close to -8. Can't draw it perfectly, but it looks like it's about -8-ish. I can't tell. Right. And notice down here, the acceleration right here is this -2. And notice this is a constant acceleration problem because the acceleration is not changing. All right, so far, so good. We know what these intercepts are. They're the initial values. Let's go back to here. All right, so we've kind of covered that. Next, the slope at any point of an XT graph is velocity, while the slope of the VT curve is acceleration. So notice this is a common thing students screw up. They grab the wrong set of rules and they say, oh, the slope of an XT graph is A. That's just wrong. The slope of an XT graph is V. The slope of a VT graph is A. Let's go see how that works out. In this case, I'm just going to try and point this out. Notice there's a large positive slope. And here we get a smaller positive slope, and now we get 0 slope. Well, if I go down here, I get a large positive velocity, a smaller positive velocity, and 0 velocity. So those correspond to these slopes up here. That's tricky. Any questions on that? Ask anytime. Slow me down. Notice we get a negative slope and then a large negative slope over here. That corresponds to a small negative velocity and a large negative velocity. So that's how that slope. Now, what about here? Here, look at this. This slope is the same as this slope, is the same as this slope, is the same as this slope, and all of those have the same acceleration. So the slope of the VT graph relates to the acceleration. It is the acceleration. So notice the slope of the VT graph isn't changing, but the slope of the XT is. And this is a very common plot for us. You'll see some sort of parabola on the XT. You'll see a linear graph for the VT and a horizontal line for the AT. Okay, that's a constant acceleration problem. All right. So that's the slopes. I'm going to pause for just a second. Any questions on that? All right. Just, oh, there's something in the chat maybe. And remember, you can ask Memo if you don't want to talk to me. All right. Sounds good. Thanks. And let's see here. Where were we? I think we're right here. So now, let's say we have, oh, so notice if you have a, I think I just said this. Let's go over this really quick. A parabolic XT graph. If you have a parabola for XT, you're going to have constant acceleration. And maybe I could have grouped these a little bit better, but if you have a linear XT, that would mean you have a constant velocity, right? Well, if you have constant velocity, your acceleration is 0. Now, putting all that together, you could think of it like this. This is one statement that says it all. If your XT graph is concave up, the acceleration is greater than 0. It's a positive number. If your XT graph is concave down, A is less than 0. You have a negative number. Let's see if that is confirmed by the experiment we just did. In this case, A was a negative number. Concave down, it looks like this case. It doesn't look like that case. So we see that a negative acceleration gives a concave down acceleration. What's really cool about this is, in general, you could describe something's motion by giving these plots, and then you don't have to show the videos. Everybody's like, oh, I could just see it in my mind. Once you get good at reading these, it's much easier to just show people a set of graphs than it is to try and do all this animation stuff. That said, both are good. Let's go back and check this again. So that was this information. So again, the trick question here is concave down is negative acceleration. Concave up is positive acceleration. What if it's linear? If it's linear, you have no concavity. Then it's no acceleration. All right. And then finally, this weird little bit, the area under an XT graph isn't useful to us, maybe to somebody else. So far, so good. Let me pause for a sec. What do you think? Any questions about that so far? All right. I appreciate your patience. Zoom sucks. I wish we were in class, but this is what we got. All right, VT graph. VT graph. V is velocity, not speed. We already talked about this a little bit. We already talked about this. The value of V equals the slope of the XT. The slope of the VT gives you the A. We mentioned that. And here's the last kind of new piece. Well, let's mention this before we get into the new piece. A linear VT graph gives you constant acceleration. So remember, if you have a constant slope of VT, since the slope of VT is acceleration, a constant slope would mean constant acceleration. Finally, look at this displacement and change in position information here. So the area under a VT curve is displacement. The area under the VT curve is change in position. It is not position. It is not distance. I cannot stress this enough. People screw this up all the time. Let's focus our time on that. Okay, so what do I mean by this? I'm going to go to the playback. Now I'm going to mention something about the simulation here. It's not perfect. The acceleration is good. Notice that the velocity gets a little numerical artifact because you have to see these little bins here. So just kind of ignore that it's not exactly 6. It's basically 6, okay? All right, and then similarly, I think the position gets a little mucked up too. Notice it's not quite -4, but that's just because it's starting here at the end of this starting time interval. So whatever, just forget that. Okay, so again, all right. And now I'm going to play this in slow-mo. And I'm going to watch this thing go. And I do want to point out the initial position of this guy is right here at -4. So X initial equals -4. And just to be explicit, I'm going to put in the units, the I hat, and the fact that this is a vector. So the initial position vector, and I'll even write the words. The initial position vector is equal to this. Got it. Now I'm going to run this simulation. I'm going to try and stop it at exactly 3 seconds. I probably won't get it right, but there we go. Oh, I got lucky. So now, in this case, this is X final vector. Oops, that's a little sloppy. I think that's 5.0 meters I hat. Right? Okay. The claim was the area under the VT curve. So the claim is that this area that I'm filling in right now should equal that number somehow. Now, what do I mean by that number? The displacement. I should be careful. So what's the area of a triangle? 1/2 base times height, right? In this case, be careful with your units. Okay, so in this case, the base is 1 second, 2 second, 3 seconds. So the base has a length of 3 seconds of this triangle. The height of this triangle is what? 6 meters per second. Keep the units in there. This is something students don't necessarily do when they're first starting, but you should do. When you're dealing with graphs, please keep the units in there so you don't screw them up. It could tell you if you grab the wrong thing, but look at this. The seconds drop out. I could clearly tell that the area has units of meters, and I think in this case it's 9. Yes. Now notice delta X is 9. Do you see that? X is not 9. Delta X vector. The change in position is 9 meters I hat. So we see that it's not the initial position. It's not the final position. In this particular case, you could say, isn't that the distance traveled? It is. However, I'm going to show you the next stage here. Okay. And maybe I'll just pause for just a second. Any questions? I'll pause. I don't see anything, so I'm going to keep going. Watch out for this next phase. Let me see if I could use a slightly darker red here. So now I'm looking at this area, right? And now we're going to have to estimate from the graph here. I'm going to say this looks to me like about -8 meters per second. You could make your own judgment. Maybe it's -7.5, maybe it's -8.5. But I argue that height is -8. Okay. So now what is the area? The area is 1/2. Ooh, wait, let me get some room here. Sorry. How much time? 1 second, 2 seconds, 3 seconds. What do you think? Maybe like
8.
I like that. 3.8 seconds. Now notice the time is something like 6.8. The change in time is 3.8. So the interval is 3.8. We do not want the time from the graph. We want the change in time over this area. So now let's just see what we get. The area should be, let's see, 1/2, 3.8 seconds. Sorry about that. And then -8 meters per second. All right, so I got to get a calculator. I don't know about you. I'm not doing that in my head. So 0.5 times 3.8 times, what was it, 8? -8? I got -15.2 meters. Hopefully you did as well. Now, what does that mean? It means we expect this thing to go -15.2, which is about right there, right? -15.2 is the change in X in the I hat. And that looks about right because I think we stopped this. So let's just keep running this and see if this works out. So we're going to start over here. Again, we start out at the blue spot. During the first 3 seconds, 9 meters displacement to the right. I'll speed this up a little bit. Now he's going to turn around, and over this next 3.8 seconds, we expect a displacement of -15. Pretty darn close. And obviously, there was an error here because I estimated. I had to read the graph, and that's common for you guys. So what I do on a test question is I jack up the error tolerance if the graph is hard to read. All right. So, all right, let's pause for a second there. Any questions about that, people? Hopefully that's working for you. So let's go ahead and stop the share for a second, clean this all up. Let's see where we're at on this list of crap we're supposed to know. All right, and so we've kind of beat down the XT graph, kind of done this. And so that's really, to me, the hardest one. You can see that's the only thing in bold there. People get in the habit of thinking the area is X, but it's not. If you know calculus, you could see these calculus formulas here. So if you know calculus, that's great. Good for you. You could use these if you want. If you don't know calculus, well, we'll learn this next semester. So I'm not supposed to do any calculus in here. I do want to point out one last thing. The value of A, that's related to the slope. We discussed that. And for the AT graph, the area under the AT curve is the change in velocity. Why don't we go ahead and do one of these slope calculations too? I don't think I did one of those as an example. Let's do one of those really quick just to make sure. So let's look at the slope of, say, an XT graph or a VT graph really quick. So how about like right here? Let's look at right here. Let's look at these two times. So let's find the slope of this. The slope of that should be rise over run, but I want to do better than in your basic math class. I want to do rise over run, but keep the units. Geez, that's a terrible S. Whatever. There. Rise over run. So in this case, if I start at this time and end at that time, let's get the rise over run. What's it look like to you? Well, let's just get this initial value. I'm going to say 2. So it's going to be something minus 2 meters per second, right? Because it's final minus initial. And I'm going to say here, this looks like negative 2. Whoops. So that's negative 2 meters per second minus, wait, this was positive 2, right? Minus a positive 2 all over. The elapsed time here is 1 second, 2 seconds. So that's 2 seconds. Gee, what do we get? Negative 4 over 2. And then look at the units. I get a meters per second, which is negative 2 meters per second squared. That's this value. Negative 2. All right, so there's the slope in case you needed that example. All right, so let's see. I think at this point, we should probably just start doing a practice question with this, right? So maybe let's go ahead and try a problem out of the workbook. Let's just look at the first one, okay? All right. So, oh, and I guess I forgot to mention this. Everybody look at this stuff too, right before we do the problem. You really need to look out for this stuff. If V and A are the same sign, these two cases, look, either they're both negative or both positive, you get speeding up. That's the trick. That's what some people have trouble with. They think that negative acceleration always means slowing down. That's just not true. Now look at this trick here. Notice these have velocity positive. Positive velocity corresponds to the words moving forwards. The reason I mention this is physics is filled with word problems. And so you're supposed to know from now on for the rest of your life, if I say moving forwards, unless otherwise specified, I mean a positive velocity. If I say speeding up, it's not clear. You have to compare the direction of motion, and speeding up means acceleration and velocity have the same sign. Slowing down means they have opposite signs, but velocity could be positive or negative. It could be moving forwards or backwards. All right, there we go. Now let's do a problem. All right, so here's a crazy looking problem. This is very similar to what we just did. We did a problem where X was concave down, the XT plot. Here's one where it's concave up. And so in this case, I know I gave you all 3 plots. Let me zoom out a little bit. The idea here is that I gave you all 3 plots. And what we're trying to do is basically what we just did on the screen. I want you to compare these plots to each other. So for example, in this one, it says, in part C, it says, determine the area from the VT curve. Compare that to the displacement on the XT curve, right? So, so the idea is you're supposed to use these graphs and compare them. And so this one, I'm going to be honest with you, it confuses a lot of students. So I would definitely use the solution with there. The idea is it's supposed to help you deal with all the weird little tricks. And so you can have the solution open while you do that. And then here you could start to do kind of a real problem where I give you a VT plot and I ask you all these questions. So the first one is going to be tricky. Why don't we start by having you guys try this out? So, yeah, take a look at page 32. Try question 2.25 right now, okay? All right, and I'll stop the share for a second. Do you want me to keep the live stream going or not? What do you guys think? Do you care?
I think you should.
Yeah, and then if something comes up, you'll have it. So apologies if anybody's out there watching the live stream. We're just doing that problem on whatever page I said. So if something comes up, we'll keep it out here. Otherwise, I guess I'm just waiting for you guys to ask me questions. All right. And you know what? Maybe we could try this cheesy little breakout room thing, right? I never do that, but so hopefully, Memo, you'll go into one and I'll go into the other, and we'll just try helping them out. Okay. Sound good, Memo?
Yes.
Okay. So, all right, we'll see how this goes.
Mhm.
Yep, looks good. Okay, so we'll try this out and hopefully it's slightly fun. If you guys are miserable, just send me a chat or tell Memo you're miserable, and that's cool. So you could join those if you want to break into smaller groups. That way, yeah. And maybe I'll join breakout room 1.